about it. Okay, already, I'd forgotten to record. That's Soraya's fault. Yeah, we're good. So the test is Tuesday. If you're watching this video tonight, whatever. The chapter 10 module at the bottom, I already talked to her in B time. Do these practice problems, watch the videos, look at your notes. You will have seen every problem, not multiple choice probably, but free response. Okay, here we go. The combined gas law is not super oftenly tested, but it could be. So here we go. The combined gas law is used to find the new temperature, pressure, or volume when you have a gas that undergoes a change in volume, pressure, or temperature. This equation right here is given to you on the AP test, so you don't have to memorize it. Now, if you look at PivNert and you look at that, what two things are not in the combined gas law? N and R, which sort of makes sense. What we're saying is we have a certain gas. I'll put in a balloon. Okay, here's a balloon. We have a gas in this balloon. We change a condition and we want to know its new conditions. But inside this, the amount of gas is the same. So N cancels out and R is a constant. So we don't need that PivNert for one condition is equal to PivNert for two. We just put P1 V1 over T1, P2 V2 over T2. All right. The combined gas law is a useful tool to solve for changes in a fixed gas. It says that changes in the fixed gas can be calculated by the following relationship. And it will give you these. It will give you 5 of the 6 variables you need. You just have to be able to plug it in. So the 1, 1, and 1, that means the initial conditions. 2, 2, and 2 means the conditions after the change.
So will they actually give us volume, pressure, and
Yeah,
They'll
they'll
give you every single
give you 5/6 of this.
Yeah.
well, yeah, that's what I meant.
Yes.
Because I was like, because to find like volume or something else, would we have to use tip there if like missing more than two, like more than one of us?
Yeah, but then it wouldn't be a combined gas law. We'd do it a different way.
All right, I'm just making
Okay,
sure.
so here we go.
On the test, are we gonna do one like the combustion reaction with water?
Yes. All right, so a child releases a balloon. The balloon rises. It wants to know the changes. So it contains originally 3.5 liters. It's at 25 degrees Celsius and it's 761 torr. Okay, now it's going to rise. It wants to know the volume. I don't know. So V equals my question mark. The temperature is 11 degrees Celsius. Whoops, I should put all these. And my pressure is equal to 685 torr. So this is pressure, temp, volume. Now you should use Kelvin here. You should use Kelvin.
And should we use ATMs too, or does it matter?
Well, I would tell you to just to keep everything similar. I don't think that one matters. Kelvin might not matter either, but I would convert everything as normal and plug them in.
Okay. Just so then we don't.
Yep. So if you look at this math, V2, I'm going to isolate that by taking T2 over and taking P2 under. And then I just plug it in.
So multiply everything except P2 and then divide it by 2, right?
Yep.
Wait, is it just the V1 divided by T1?
Or is everything divided by two?
Oh, T1 is on the bottom. Sorry. Yes. Sorry. Like it's on the bottom here, but the way I wrote it has a little, it looked a little tricky. You are right. Sorry about that. All right. We have an answer.
Almost 1 second.
What?
3.7.
3.7 liters. Anyone agree with that?
Yeah.
All right. Sounds good to me. I don't know the answer, but it seems reasonable. All right. It got colder, so it should get smaller, but the pressure decreased, which should make it get larger. So it should be a number pretty close to the original one. There's no direct relationship like to predict, but it's not super crazy. So it's most likely correct.
So, which, okay, but I did it right. That means I can say the thing.
Yes.
I already forgot.
Can we only do this on the test? That.
No, different,
No.
different thing gave you extra credit in another class.
Yeah. He knows what it is.
We have taught the chemistry, and we
We have met the chemistry.
we have met the chemistry
Made it hard.
and made it ours.
Yeah. Because we have to get credit. Why are you getting credit for that?
Thank you.
I'm confused.
Ask her, Law.
On that or my math?
No, not on the map.
Okay, then I'm moving on.
Wait a minute. I can tell. I'm confused about the water though. And the hard question.
Yes, sir, Cooper Lloyd.
I'm gonna check it.
I gotta run the girl watch because I ran special. I lost the special pen.
A
Sure.
special pen.
Okay, here you go.
Black tar heroin pen.
It's his needle actually.
Okay, fire away right here. A gas originally at 27C, 1 ATM and 3.9 is cooled at a constant pressure. What do you mean by, what does it mean by constant pressure? Pressure doesn't change. So it doesn't look like it gives you two pressures, but it does. They're both one. What's that? Yeah, you should go to Kelvin.
Well, this one's easy.
Yeah, this one's a lot easier than the other one.
I'm not time dumb. But I don't think I am. But I don't think people that are dumb know they're dumb. So could be me.
It's the same setup, right? Yes.
What did you guys get?
Oh no. I can't focus right now. I got 3.6.
Yeah, I got 3.679 liters.
Did I
Bless you.
transcribe that right?
Yeah.
That
Bless you.
Bless you again. And you got what?
3.679.
3.679. Yeah, I got that. Yeah, I got
Okay, I might have.
I did not get that.
What did you get?
3.46.
Interesting.
Getting like no,
Are you converting things?
like
Like 300 Kelvin? Then
Something on top that wasn't supposed to be.
are these in parentheses?
Oh shoot, I realized what I did.
Then I don't know what you're doing wrong.
We have that basically the same.
Tolman, turn around and check his calculator for me.
I was 1,000th
Okay.
off, Caitlin, 5.9.
3.692.
I got 4.1.
Yeah.
Oh no, we're we're all in trouble.
Well,
Okay.
majority of us got 3.68/9.
Okay, that's probably the right answer. Let's just double check. T2 is what number?
One. Oh wait, no, that would be
No, that's not
T2 would be
Yeah.
283, and then T1 is 1, and then 3.9 is
284. 284. That's probably why the small difference.
Yeah, it's 284.
Yeah, that's.
P2 is 1 again. T1.
Oh, I know you're right. Never mind.
Okay,
That's like a million times more confusing to rearrange it.
sorry. Well, you don't have to.
Just algebra.
No, yeah, no, I know, but it's like more confusing.
Hey, whatever works for you guys, do it.
Okay, yeah, I know what you're wrong.
Okay. All right. That's the combined gas law. I'm moving on with my life. Okay, most of, well, not, I don't know, I'm not even gonna finish that sentence. Here we go. Kinetic molecular theory, also known as K-MOT once in a while. This is a model that aids in our understanding of what happens to gas particles as environmental conditions change. So it's just a model. It's really common sense. So don't overthink this one, even though it can sound a little confusing. Here we go. So the main tenets of kinetic molecular theory is that gases consist of large number of molecules that are in continuous random motion. So they're just bouncing around everywhere. This room is full of a gas and the particles are moving wherever they feel like. Pretty easy. It's random. You know, we don't have a direct flow one way or the other unless there's like a pressure difference. Then it will go from high to low. But just typically, that's wind and air currents. You're creating a vacuum in your lungs. So a negative pressure. So air's pushing into your lungs. Okay, we all right so far? Now, these things, they very often test these little nitpicky things. The combined volume of all the molecules of the gas is negligible relative to the total volume in which the gas is contained. So yeah. So what that means, it's another way of saying that gases are extremely not dense. That was probably a stupid way to say that. Gases are not very dense. If we took all the mass of the oxygen, nitrogen mostly, and all the other things, and we pushed it down and made it super dense, you know, we'd have less like oxygen molecules than the bucket over there of safety glasses, like way less than that. But all that is occupying here, gases spread out a ton. All right, then it's important to know this one. The attractive and repulsive force between gas molecules are negligible. So that means they just fly by. They might hit each other. You know, there might be one here that runs into that, and they just bounce off. They don't stick together. All right, they just go about doing their business. They interact with something, they bounce off. They don't stick together.
Well, what about diatomic ones?
They would already have been reacted, so it would be an O2 molecule flying around.
And aren't those technically bigger and more like, oh no, they'd be,
Okay.
they're not attractive at all when they're diatomic, right?
Right.
Don't be rude to them, please. I'm sure they're kind of attractive.
Okay. Anyway. Okay.
You don't have to do them like that, guys.
Energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time as long as the temperature of the gas remains constant. Okay, now this sounds a little tricky, but what it means is this one right here, it might be flying super fast. And then it hits this one, and this one goes this way. This one will say it comes this way, and it seems slower. So it can impart energy to another one, but the total energy of all of them, as long as the temperature stays, is pretty much a constant. Yes, Coop.
So this would have to do with like ideal gas law a little bit, or like
All right,
yeah,
this
isn't there some stuff that it like says like that not everything is always like perfectly aligned?
right. We are describing an ideal gas right now. Now, there is no such thing as an ideal gas, but they are so little difference that we don't care. It's like when you take physics and you drop a pencil, you can do the math and you're going to calculate how long it would take to fall. And you are ignoring the fact that there's air resistance, because air resistance might change how hard, or sorry, how long it takes this for it to fall, but it's going to be like a 10,000th of a second. It's so meaningless. And so the gases that we deal with are so closely modeled with an ideal gas law. We just go with it and it makes life easier, a ton easier for the math. What?
There's just almost no difference.
Yeah, and it depends. You'll see here in a second when they do deviate, because that is a section. But we don't have to deal with them too much. All right. You have to know, not this exact sentence, but you 100% need to know that the average kinetic energy of molecules is proportional to the absolute temperature. All we're saying is the energy is related to temperature. I feel like we said that in the first chapter, but it's super, super important. All right. So this graph's a little bit confusing, but the higher the temperature, the greater number of particles you have with a higher energy. That's all that's trying to show you. All right, so the kinetic energy and the temperature are directly related. All right. Okay, there are a few applications that we have to make sure we know. This word's probably new to you. That was not a very good underline. This will be way better. And it's called effusion or molecular effusion. And this is what led to your depression as a child when you woke up the next day and your balloon didn't float anymore. That's like life changing. Well, it's effusion's fault. Effusion is defined as the escape of gas molecules through a tiny hole into an evacuated space. So the balloon's made out of rubber, which to us is pretty impenetrable. But when we're putting in a helium atom, it's the second smallest atom on the entire periodic table. So it's so small, it can wiggle its way through the lining of the rubber balloon and escape out. I guess the way I drew this, it should be that direction. And so the more dense, larger molecules stay inside the balloon and the helium escapes, and so the balloon doesn't float anymore. Okay, you need to be able to know and apply this. Smaller and less complex molecules have a faster rate of effusion than larger, more complex molecules.
Based off of like molecular mass, or like how many atoms are actually together?
It's mostly related to its mass.
Okay. Because like on this, I feel like I would see that that may be a
The greatest rate of effusion, you should definitely not choose C. That would be slow. Yeah, but it's heavy. It's big, big, big. Okay, so the following gases, blank will have the greatest rate of effusion. So which one would escape the fastest?
It would be A. No, wait, no, C. B. B. B final answer. E. B final answer. Wait, no, what's VR? Oh, VR is 7. VR is heavier than CL. Yeah, so it would actually be, it's gotta be 17.
Okay, kind of tricky. So smaller and less complex would be A. Well, why, explain to me why you think it's B.
Because it's smaller. And the H3 would be 17, roughly 17.
It weighs less, but it's not
The other
smaller.
one's 16.
17 and 16. So we end up with a battle between, we have a little bit bigger, but we have less complex is here. And so it is NH3.
So are noble gases normally slow?
Yep. Okay, now on the exam, these are farther apart, so no one argues with me. Okay? No. Okay. No.
Normally really slow, effusion?
Yeah, they're huge. Argon is 40, right? Element number 40.
Yeah, well, it weighs 40.
Yeah, it's sorry. Yeah, thank you. Its mass is 40. That's really large. 20 protons, 20 neutrons. You could fill a balloon full of argon and it would stay inflated a very long time. Okay, now who's ever seen the shiny balloons that float forever? Of Mylar. Yeah, Mylar balloons pretty much float forever. You can go to Walmart probably right now and see 2 or 3 of them on the ceiling. They've never been able to get down. I mean, they could like throw a dart at them or whatever, but they stay up there forever. Is that because they're full of a different gas? No, it's the material. Mylar is, no, it's microscopic, but it's really, really, really thin layers of very tightly packed stuff. So it doesn't get through.
Which ones are we talking about? Which ones are those?
The,
Like sweet
the
16?
shiny, yeah.
Oh, okay. I was like, I'm pretty sure that's what we're talking about.
Wait,
but not-
you know those like racks they have at the top where they just have a bunch of balloons in the white circular thing?
All right.
Okay, have a bunch of helium balloons.
Next is diffusion. What? This is the same thing. Whatever you want to say. Potato, potato. I often say things because I suck at spelling and I've had to learn to say them how the next letter is. So if I say diffusion, it's because I want to write an I instead of an E. Just trust me, it's my brain. All right. Diffusion, if that makes you feel better. That's the spread of one substance throughout a space or throughout a second substance. You learn this, if you're like my children, you learned it in like 3rd grade, 5th grade, 6th, 7th, 8th, 9th, and 10th grade. So diffusion, pretty simple idea. Like if I light a match, the smoke around the match is not going to stay around the match the entire time in a cloud. It's going to spread out throughout the room and fill it completely. If we put food coloring in water, and just let it sit over time, it diffuses or goes throughout. Now that's a liquid, but in gases, it's the same and even faster.
Like Febreze or Axe.
Yeah. So anyone ever bought really nice, expensive lotion and it smells great,
Yes.
but the smell fades? The more scented it is, the faster the scent goes away.
Really?
Yeah, because you put the lotion on, it's designed that you're like, wow, this smells so good. And everyone around is like, wow, Reese smells so good. But the reason it smells so good is because it's made out of super small, low complex molecules that diffuse quick. But the problem is if it diffuses quick, it also leaves your hands quicker, and so you reapply. Yeah, the smellier it is, really is the smaller it is and the faster it diffuses. All right, so it's the same thing here. Smaller and less complex molecules have a faster rate of effusion than larger, more complex molecules. Because they,
Basically anything smaller is faster. Is what it's saying.
yeah, like the crowd at Disneyland. Some dad pushing a double wide stroller. This is my life. moves through Disneyland traffic a lot slower than Derek and Dallin did. Like, I needed more space. There's tons of interactions I had to move around, and people got ornery. Yes.
I just want to say, Disneyland, it is so easy to see who's LDS.
It does. It's pretty simple, but we won't go there.
Yeah,
I'm
like,
confused.
I don't know, just like goldfish to kids and crap.
Yeah, tons of kids, no tans, BYU,
And like,
everywhere.
yeah. Like, we literally got on.
We're predictable.
We got on It's a Small World once, and like these two old people like said, it was like a couple years ago. We were all like little kids, but they're like, "Hey, you guys LDS," and they were from Utah too. It was funny. Like,
Yeah.
you just see-
The only white people you see wearing cargo shorts,
From Utah.
you know what I'm talking about. With white socks. Like, oh,
Almost see my socks.
hey, Dad. Anyway, it looked cool in 1992. All right. Real gases. In the real world, the behavior of gases only conforms to the ideal gas equation at relatively high temperature and low pressure. All right.
Oh, is it because it's moving faster?
Yep. Which keeps them farther apart, less attracted to each other, greater collision, so more elasticity. And then if you have high pressure, let's reverse it for a second. If you have high pressure, so here's your container and they're all just bouncing around. Then we increase the pressure by like pushing a piston down. You okay with that? Now the dots won't compress, but just pretend they do. As I push down, suddenly all these dots are really close together and they are more likely to have an interaction between each other. And honestly, if you think about it, as I compress, they won't even be a gas anymore. They become a liquid.
So if you put enough pressure on something.
Hold on, she started first. What?
If you put enough pressure on something, it could like become a liquid without needing temperature change. Or
Yeah, absolutely.
Is that how like aerosol guns and stuff work with the little tanks? Of like pressurized air?
It's really high pressurized air, but I don't think
They don't
it's.
get all the way to liquids,
I don't
do
think
they?
it's liquid. I don't think so. If you drive on the freeway very often, daily, you'll pass LNG trucks. Hold on. Liquefied natural gas. Because you can transport a ton of natural gas if you liquefy it first, because it doesn't take that much space. So they do that. There's trailers. They look kind of weird. They're like a bunch of tubes stacked on top of each other. And those are full of liquefied carbon dioxide typically. Go ahead.
It's also like compressive liquid, like water filled with solid.
Yeah, theoretically. Water's really hard to do that too, but theoretically we can, yeah. Okay.
that was any element, right?
All right, yep. So now listen. This is a must know. You must know when real deviates from ideal. Okay.
Like relatively high pressure, high temperature.
So that's not, I don't know, relative, even room temperature now, we're pretty close to an ideal. So anything above 25, honestly.
Wait,
Like 25 Kelvin Celsius or whatever.
Sorry, that'd be Celsius.
does temperature, doesn't temperature make pressure go up?
Yes, it can, for sure. Okay, so you need to know in this exact thing, the behavior of ideal gases only conforms to the ideal gas equation at relatively high temperature and low pressure. So if we decrease temperature and we increase pressure, we become less and less ideal. Okay, Cephalo, what can I do for you?
Oh, I'm just gonna wait till the new class and talk to you.
Okay, sounds good. All right, now, here are the reasons. And I already drew it out, but the assumptions made in the kinetic molecular theory model break down at high pressure and or low temperature. Once again, as things get closer, that's a terrible color. As things get closer, they start to interact with each other. Gases don't interact with each other, liquids do. So under higher pressure, the gas becomes less gas-like and more liquid-like. That is a departure from the ideal gas law. There's still a collision, but now it's less because there is an attraction as they go by. So if I had a hall full of kids and none of them had a crush on each other or were friends, they're going to move pretty quick. But we all know all it takes is some couple at the bottom of the stairs and the whole system breaks down, right? Even exiting my hallway can be affected by a bunch of friends at the bottom of that stairs choosing the worst place for conversation. Then we all have to go around. We behave more like a liquid where we're closer to each other and less like a gas where we're free. No, I don't believe that. Okay.
I was like, y'all really be going around?
Okay.
I was like,
Here we go. The ideal gas equation can be adjusted to take these deviations from the ideal behavior into account. You should know that after 2013, you are no longer tested on this math, which you should be very grateful for, but you should at least know the name of it. The corrected ideal gas equation is known as the van der Waals equation. Now, a van der Waals force is a weak interaction. It's named after the same guy. So you don't have to do it, but here is Pivnert for a real gas. Don't write it down. It gets more complicated. So well, I'm sorry. That makes me feel sad inside. All right, so these are where we adjust to make our real gases and our ideal equation match each other. But please don't waste your time writing it down. You would find these values of A and B in a table. They have to be given to you because they're different for every single substance. All right. So you don't, Mr. Van der Waal.
Well, yeah, what did you do?
Or Mrs. I don't know.
didn't we learn this in AP Bio?
You may have. All right, I have some good news for you.
It's the end.
But there's an asterisk.
Oh no.
There's always math practice problems we could do.
Okay, I need these, so everybody stop.
Reese said, everyone shut up right now.
There you go. There you go, Reese. This is the one you want.
Yeah,
I did
the
this
hardest
myself.
one.
Is this the same numbers?
Yes.
What? This problem, oh yeah, it is right there. This is number 4 on the practice one.
Yeah, it's the exact same.
Were those other ones, were those gonna be on the test or were those a different chapter?
Wait, is this the
Number
P-
4 will definitely be on the test, and a problem like this will be on the test. Now, those are the 2 main ones, but I certainly can ask you easy ones as well.
Can I have a second problem?
This?
The one that you were like, this one will also be on the test here.
Okay, well, I love that you're all taking pictures of them, but remember, they're all online.
Is that one?
It's being recorded too, right?
This one's online because we already did it like a week ago.
And then on the one we're supposed to be doing, this is the P1.
Okay, so I'm going to go back to this one because Reese wanted it.
I also want it.
All right, Greg, they're just going to be chatting now. Come on up. I'm going to stop recording. It's fine. The numbers will be different. Okay.